So hi, welcome to discussion 12. So in this discussion, we'll introduce the concepts of inspection analysis. This is what Professor covered in last week. So basically, we'll introduce you an easier way to analyze your circuit and find the small signal model to find the small signal gain. So this is another way to find the gain. V out over Vi. So instead of doing the hybrid pi model for BJT or MOSFET, you can use inspection analysis to find V out over Vi. And then I'll also introduce an important concept called current mirrors. If you learn 140, you will know, so it's all about current mirrors. So first, let's introduce the concept of inspection analysis. I mean, how we use it. So first, you have a BJT like this. This is your base, collector, emitter, and you have an RC, RE. If we draw the small signal model of it, yeah, so for this part, I ignore those DC biases. I just put a single transistor here, and I want to draw the small signal model of it. So the small signal model would just be, I'll have a BS as an AC voltage source, and I have my RS as an input signal resistance, and I have my RB, which is usually the biasing circuit, so it's R1 in parallel to R2, and also BJT. So I did not use the hybrid pi. I did not draw the hybrid pi here. So I still put a single BJT here. So it's my MOSFET, and this is my output. So this is my base, collector, emitter, and I have my RE, also ground. Here I will have my RC to the ground. This is the small signal model. I may also have a R load as a load resistance. So this is the small signal model of the circuit. The only difference between what you have learned is I did not replace the BJT with the hybrid pi model. I still put the BJTs here. So the inspection analysis will just basically do some derivations, and you will know some expressions for resistance and gain of your circuit. So by doing some analysis or derivations, you can just refer to Professor's last week's lecture. He just defined 3 different resistance. This is called R small c. This is called R small e, and this is called R small b. So R small b, R small c, R small e, those are referred to the equivalent resistance looking in some directions. So the RB here, this is the base resistance or equivalent resistance when viewing from base to the right. So at the base, if you're looking to the right, so equivalent resistance is called RB, R small b. And for R small c is the equivalent resistance when viewing at the collector to the left. And R small e is the equivalent resistance when looking from the emitter to the top. So RB, RC, RE here are all equivalent resistance. They are not the actual one. So they're just equivalent. The definition is R small e is 1 over Gm. Actually, there's some small part in the RE, but I just ignored it. If you won't remember it, you can remember the full expressions, or you can just think it's 1 over Gm. This is R small e. Remember that. And RB, R small b is R pi plus beta plus 1 times R capital E. So it's a resistance connected to your emitter, R capital E. Remember this. And your RC will just be RO, small signal resistance RO, plus GM times RO times R capital E. Remember this? And also, we have also, so right now we know the resistance at 3 different ports, the equivalent resistance. And for inspection analysis, you have also need to define what's the GM. This is called transconductance or conductance, transconductance. So GM is called transconductance. Transconductance. I'm sorry, I'm not sure it's called conductance or transconductance, but I'll just use GM here. So the capital GM here is used in Y parameter model. So I'm going to introduce a model called Y parameter. So you have learned the hybrid pi for BJT and something like that, but Y parameter model is a different one. This is defined for 2-port system. So that means you have an input port and an output port. I'll just draw it here. So you have a port 1, and you have an R, let's call it Ri. Then also you also have a current source is capital GM times V1, and an RO here. This is a port 1, this is port 2. So it has V1 and plus minus V2. So this is the Y parameter model. And for how do we use it for BJTs? We'll just say the port 1 here is a base. And port 2 here, it could be the collector or emitter or whatever. So if we want to find, so I'll use one example. If we want to find the gain between base to the collector. So between what's the gain between base to the collector? That means we want to find what's the VC over VB. In this case, you will replace your port 1 with your base. So your base is port 1, is your input, and your output port will be the collector. So this will be C. And what's in other words, the V2 here will be VC. And your V1 here is your input source, it will be VBE. Right? So what's your VC over VB? It will just be, you have V1, and this current source is GM times V1, and you have resistance R naught. So your VC will just be, so your VC will just be negative GM times V1 times RO. So your gain VC over V1 is VB, okay? So it's negative GM RO. So if you want to find the gain between 2 ports, like you want to find the gain between base or collector, you just need to find what's the RO and what's the GM. So if you find RO and GM separately, and then the product and take a reverse value, will just be your gain. And RO is simple. For base to collector, we know RC, right? Is this. And so your RO will just be R small c in parallel with R capital C in parallel with RL, right? So let's take a look here. So you have RC, R capital C, and RL. These 3 are in parallel. So your RO, definition for RO here is V2 over I2 when V1 equals to 0. Basically, the output resistance. The output resistance is just R small c in parallel with R capital C in parallel with RL. That's your RO. And what's your GM? The GM, the definition for GM, I mean, this is true. This definition is true for all Y parameter model. So GM is always I2 over V1 when V2 equals to 0. That's the definition. And that's how we calculate the GM for different models like base collector, base emitter, emitter collector. So basically you have to ground your output port first. That means you have to ground your V2. And then you give an input signal V1 to the port 1 here. And then you calculate what's the current I2, what's the current on the second port. So what's the, if you have a V1, what's the I2? And then you take the ratio, you get GM. But for GM, basically the derivation is also shown in professor's lectures. You don't need to remember it. You don't need to derive it by yourself, but you have I would suggest you to remember it. So the GM for different circuits, you may want to know it. So for the GM for base to collector, let me copy this. Okay, let's say this. So base to collector, the GM. So you want to find what's the gain between base and the collector. What's the gain? The GM is small GM. This is a parameter you defined using your DC biasing current. So the GM is IC over VT. And your R pi is beta over GM. And your RE, small e, would be alpha over GM, something like this. So base to collector capital GM will be GM over 1 plus GM times RE, R capital E. So it's an external resistance. And your base to emitter, it has another GM, but we'll leave it to the later. And the emitter to collector. So you find the gain between emitter to collector. And your GM will be negative GM. So recall what I defined before. The actual gain using the Y parameter model is negative GM, negative capital GM times RO, where RO is our output resistance. It's the output resistance. And your capital GM is what we define here. So what's the final gain? So what's the final gain? Base to collector will be negative GM R naught, which is negative GM over 1 plus small GM RE times R naught. And R naught is R small c, is this one, the equivalent resistance, in parallel with R capital C in parallel with RL. This is your equivalent output resistance. And your base to emitter, this is different. So we find the gain between base and emitter BE here. We're using the other model, it's called T parameter model or T model for BJTs. But this is pretty simple. You just need to remember it's the VE over VB. So the gain between base to emitter is just R capital E over R small e plus R capital E. And R capital E, the RE or R small e is alpha over GM plus RE. This is really small. So alpha over GM is small. So you can just say base to emitter, the gain is 1. So that's how we call this kind of circuit. Base to emitter is a source follower. So VE is usually equals to VB. These are just equal. The gain is 1. And for base, sorry, not base anymore. The third possible situation is emitter. Is emitter to collector. So the gain between VC over VE. This is negative capital GM R naught. And the GM for emitter collector is negative GM. So negative becomes positive. It's just small GM times R naught. Right, and the R naught here is usually RC. Yeah, you can do some circuit analysis. This is usually RC in parallel. It's actually RC in parallel with R naught. You can draw the circuit and find what's the output resistance. It's usually RC in parallel with R naught, but when R naught is large, so R naught here is VA over IC. If it's large, then it will just equals to GM times RC. And RC here is R capital C, so it's an external resistance. So the key point, I mean, you have to at least know this. The base to collector gain is negative. So we will have a negative gain. We will invert your input signal between base and collector. And you will have the gain equals to 1 between base and emitter. So BE will have almost the same voltage. So you have the same voltage for base and emitter. And you will have a positive gain between emitter and collector. So this part, let me draw it using another. Okay. So you just need to know collector to emitter. This is positive gain. Base to collector is negative gain. And base to emitter is 1. So just remember it. This is how we do the inspection analysis. And we'll do one example here. So this is the example. Yeah, it's a simple circuit, single transistor circuit. And for this, so nothing is given. You have to find GM, R pi, and other things by yourself. So GM, R pi, R naught, all by yourself. So first, we have to find the DC biasing point of the circuit. So VI here is AC, but we have a DC VBB. This is a DC. So let's do find the DC biasing point first. That means we have to do a KCL or KVL in this direction. So you have VBB minus IB. So I assume the current here is IB times RBB minus VBE equals to 0. And your IB will just be VBB minus VBE divided by RBB. So if you assume the turnout voltage like VB is 0.7, you get IB equals to 0.023 milliamps. And that will give you beta equals to 100. So your IC will be beta times IB, which is 2.3 milliamps. Pretty simple. So what's your DC operating point VC? So V capital VC as a DC voltage at your output. You'll just be VCC minus IC times RC, which is 3.1 volts. So DC part are simple to calculate. So using the DC biasing point, you can calculate GM is IC over VT, will give you 92 milliamps per volts. And your R pi will be beta over GM. So just 100 divided by GM, which is 1.09 kilo ohms. So we are done with the DC part and also the small signal parameters. The next thing we have to know, we want to know is what's the Vout or small Vout. We want to find what's the output resistance. So that means you have to find the gain between Vout and VI first. VI is here. There's another voltage divider between. So this will equals to Vout over VBE. So VBE is here. And times VBE over VI. And VBE over VI is pretty simple to calculate. It's just a voltage divider. So VBE over VI would just be R pi, right? So let me draw it. This is your VBE. And you have an R pi, a small signal R pi here. So your VBE would just be R pi over R pi plus RBB. That's simple. And then I want to use the inspection analysis to find what's your Vout over VBE. So recall the inspection analysis we did before. So is usually negative GM times RO, R naught. You have to find GM and R naught for the circuits. You have to recall, so the V out here, the output here is at the collector, and your input is at the base, right? Your input is at the base and your output is at the collector. So basically we are doing a base to collector circuit. Base to collector circuit. And the GM, or capital GM for base to collector circuit, is small gm over 1 plus gm times RE, capital E. And the thing is, we don't have a RE in this circuit. There's no RE, just the emitter just connecting to the ground. That means RE equals to 0. So your capital GM will just equals to your small gm. And what's your R naught? So recall the inspection analysis. What's the small RC? R small c. So the R small c is the equivalent resistance from the collector looking downward. So R small c is RO plus GM RO RE, and your RE equals 0. So it's just small RO or R naught. And your capital RO, the output resistance will just be RO in parallel with RC, right? So choose another color. So you have an R small c. Okay, I'll draw it in another position. So you have this is an R small c here, the equivalent resistance, and you have an R capital C, the upper part, and this is your V out. So the equivalent resistance or output resistance here will just be R capital C in parallel with R small c. So you have to play with the resistance here. And if we see R naught is large, if we have the small signal resistance is large, you can just say that R naught will just be RC or R capital C. So what's the gain? Your V out over VBE, the base to collector gain will just be negative capital GM, which is small gm, and your RO will just be R capital C. It's pretty simple. It just is negative 276. So you don't need to draw the hybrid pi model and do any those small signal models or small signal analysis you have done before. You can just use the inspection analysis to find the gain. And then your final gain over VI will just be negative 276 times your R pi over R pi plus RBB. Just plug in numbers, you get negative 3.04. So it's done. You have the DC V out and also the small signal V out. So this is a pretty simple, just a simple example for how we're using inspection analysis to analyze the circuit and how easy it could be. You just need to plug in numbers, right? So if your RE equals 0, just plug in here and you get your capital GM very easily. Okay, more complicated one. So what you have seen before are just single transistor circuits, and now we have a two-stage, or we have a multi-stage amplifier. We have 2 transistors now, and we want to find what's the V out over V sig. So what's the gain for the whole circuit? I'll give you some parameters. So for this circuit, Q1 and Q2 are the same. So they have the same GM, R pi, RE, all the same. The GM is small GM is 40 milliamp per volts. And you'll have R small e, which is R over GM, is 25 ohms. And your R pi is beta over GM, is 2.5 kilo ohms. I also give you R sig is 4K, and your RL is 4K. And you can ignore are not. So small signal resistances, it can be ignored. So first, I want to know what's R into. Just using what the expressions were defined earlier for inspection. So the R into is the resistance looking to the base of Q2, right? And you recall what's the R small b, the base resistance is R pi plus beta plus 1 times RE. And RE for this Q2 is 0. So it just equals to R pi 2. Sorry, R pi 2. It's a R pi for the second transistor, Q2. And next step, I want to find what's the R in one. So here, or what's the R in, is the small signal resistance or equivalent resistance looking through the base of Q1. So this is just RB1. And we can still use the expressions we defined earlier. It's still R pi 1 plus beta plus 1 times RE. Well, in this case, what's RE? Is the resistance at the emitter part. Is your RE. And your RE is actually R into. So it's R pi 2. You have a non-zero RE now. So what's your R in 1? For R in will just be R pi 1 plus beta plus 1 RE, which is R pi 2. That's simple. Just use the expressions and spectral analysis, plug in values, and you can get this. So our in is 255 kiloohms. Calculate this. This is 2.5 kiloohms. So resistance are done. And we want to move on to the gain part. So I want to know what's the gain. That means I want to know what's the V out over V seek. So V out over V seek can be divided into several parts. So this is actually VB1 over V seek times VB2 over VB1 times V out over VB2, right? And your VB1 over V seek is just simple. So VB1 over V seek is just a voltage divider. So your VB1 over V seek is R in over R in plus R seek. And we have R in here. It's easy. This gives you 0.98 volts per volts. And what's your VB2 over VB1? So let's say what's your VB2 over VB1? Your VB2 is here. This is your VB2, and this is your VB1. What's the corresponding model to it? This is from base, the gain from base to emitter, right? This is a base to emitter. And we have defined before, so for the inspection analysis, we say the base and the emitter are just called source follower. So the gain between them are just 1. So you can just say VB2 over VB1 is just 1. Or you want to be more specific or more accurate. This is actually equals to R capital E over R small e plus R capital E. And your R capital E is R pi 2, right? And your R small e is defined here is 25 ohms plus R pi 2. So this is very similar to 1. If you plug in numbers, you get like 0.99 volts per volts. So it will not hurt if you just say base to emitter is a 1. So if you just use 1, it's okay. It's correct. But if you want to be more accurate, like plug in R small e or R capital E to calculate the gain, it's also okay. It's just your choice. And the next one is V out over VB2. So V out is here, VB2 is here. So this is from base to collector, right? So what's the gain between base and collector is negative GMRO. And the GM we have defined earlier is small gm over 1 plus gm times RE. And your RO is R small c, and parallel is RL. The thing is your R small c is what? Is RO plus GM RO RE. And just for this circuit, we'll know RE is 0 because the emitter is connected to the ground. So there's RE equals 0. So just plug in RE equals to 0 to this circuit, you get VO over VB2, the base to collector, will just be negative GM times RL. Yeah, as I said, ignore RO. So R small c in parallel with RL will just be RL. So again, it's just negative GM RL, which is negative 160 volts to volts. So your final gain, V out over VC, will just be the three products, right? We have calculated before, will be negative 155 volts per volt. So yeah, I just still want to say it again. Is base to collector will give you a negative gain. Base to emitter will give you 1, which is a positive 1. And emitter to collector will give you a positive gain. So sometimes the sign are really important. So I would suggest you to remember this at least. Okay, so that's all the examples I had for inspection analysis. We can move on to current mirrors. So this is what you have seen here. It's a simple current mirrors for BJT. This is a BJT current mirror. So why do I say this is a current mirror? So the current mirror is usually used for biasing circuit. It's used if you want to bias your circuit, you can use a current mirror to doing that. So you just need to put a reference current source to one part or one branch of your circuit. So for example, I just have my I reference on the left part of my circuit. And then I can make my I out equals to I ref. So this is called a current mirror. So basically, these two branch are just like a mirror with each other. So these two branches are almost the same. They have the same current. So that's called a mirror. That's how. So I will introduce it here. So why do we say those two are mirror current mirrors? Why they have the same currents? So the thing is, you have an IRF here, and this IRF will be divided into two parts, right? Is IC in the, this is IC over beta for the base. But the thing is, the two bases are connected with each other. They are directly connected to each other for Q1 and Q2. If we say Q1 and Q2 are the same, and their base are connected, and their emitter are all to the ground, that means the VBE2 equals to VBE1. The VBE for device 2 equals to the VBE for device 1, and they are the same. That means your current IC will be the same for two devices. So for Q2, you also have an IC flowing downward. If you have an IC flowing downward, you must have a base current which equals to IC over beta. That means this part, it will be 2 IC over beta. So you have to connect your base to the emitter, or to the collector. So for current mirror, we usually have we will have a wire to connect between your collector to the base. So it's usually connected for the mirror part. So total current here will be IC 1 plus 1 over beta. And this is same IC 1 plus 1 over beta. This is your IE. So this is the current mirror. So if you bias in one part of your circuit correctly, you will have the same current in the other half of your circuit. So this is a mirror. This is a BJT current mirrors. It's pretty simple. And then this is, we will also have a MOSFET current mirror. So this is the current mirror for MOSFETs, or N MOSFET. So for N MOSFET, the thing, one really important feature, the difference between MOSFET and BJT is that for BJT, you will have a base current, right? But for MOSFET, the current to the gate will be 0, because so this is the MOSFET. You have a metal oxide, right? You have oxide and your substrate. So and this is your metal, metal and oxide. This is your substrate. And this is your IG. Because there is an oxide connected, like in between your metal and the substrate, and oxide is insulator. So your IG must be 0. There's no current that could be flowing into your gate unless there are leakage current, but we don't include it here. So IG just 0. That's the difference, or one of the important difference between BJT and MOSFET. So even though we connected the gate to the drain for the current mirrors, there's no current to the gate. So the current here is 0, no current flowing into the gate. And so basically your IREF reference, which is equals to ID, right? ID is usually mu n Cox W over 2L VGS minus VTN squared. If I say Q1 and Q2 are the same, that means they have the same mu n, same Cox, same W over L, all the same. So let's say the mirror part. Those two, Q1 and Q2, the gate are connected to each other, and their source are connected to the ground. So VGS1 equals to VGS2. And your Q1, Q2 are the same. So you have the same mu n Cox W over L, same VTN. That means, and now you have the same VGS. So your ID will be the same. So ID2 will equals to ID1. So this current will also be ID, will also be IREF. Another current mirror. So you have the same current. And I'll ask you one question, the last question here. So you know the two branches have the same current. What if I give you IREF equals to 100 microamps? And I know my Kn prime. Kn prime is really mu n Cox. Yeah, just mu n Cox equals to 200 microamps per volt squared. And my W over L equals 10. So this is all the specs I gave to you for the circuit. And I want to know what's the lowest possible value for V out. So I want to know if this is the V out. I want to know what's the lowest possible value for it. What's the lowest possible DC value for it? So the thing is, let's see here. So for the current mirror, why we always connected our gate to the drain? So we connected gate to the drain. We make these two nodes connected is to make sure the device is in saturation. So recall how we find the saturation regime for MOSFET is when VDS greater than VGS minus VTN. If you connected your gate to the drain, that means your VDS will just equals to VGS. It must be greater than VGS minus VTN. So this device always in saturation. This is cool, right? Always in saturation. This is an important feature for current mirror. We're trying to make it, for MOSFET, we try to make it in saturation regime. So what's the lowest possible value for V out? That means your V out at least should be greater than VGS minus VTN. We want to make it saturation. And the lowest possible value, like V out mean, will be VGS minus VTN. That's the lowest possible to maintain the saturation operation of your MOSFET. And we can use, one feature of current mirror is that they always have the same current, like ID2 equals to ID1. So your ID2 will be a half Kn prime, right? W over L, VGS minus VTN squared. ID2 equals to ID1 equals to IREF. And Kn prime is given, W over L is given. So you can just plug in numbers, you can find what's the VGS over minus VTN. The VGS minus VTN is 0.316 volts. So your lowest possible value of V out will be VGS minus VTN equals to 0.316 volts. So this is one simple question about current mirrors. So you can use current mirrors to find what's the lowest value for V out to make the device remain saturation. Yeah, you will learn more about current mirrors and also multi-stage amplifier. I mean, instead of just using one single transistor for your amplifier, you may use multiple of them, like 4 transistors. So you will learn more about this either in this week or next week. You will learn it in this class. Yeah, and that's all I have for today. If you have any questions, you can ask, or you are free to leave.